This is a presentation investigating an electric motor and magnetic forces by Kayla, Grace, and Dria.
We will be focusing our investigation around the question that states, what effect will a change in current have on the number of rotations per minute of a wire loop? Our goal was to be able to relate current, magnetic force, and magnetic field to our experiment. We designed an experiment that would contain 3 trials in which the number of batteries increased with each trial. We hypothesized that as the number of batteries increased, the number of rotations of the wire loop would also increase. After completing our investigation, we confirmed our hypothesis to be true. We used 2 main models in our experiment. The first was the equation F equals IL times B. In this equation, F is the magnetic force, IL is the current, and B is the magnetic field. This equation showed us that the current flowing through the wires, which originates from the batteries, is multiplied by the magnetic field created by the magnets. The magnetic force is the result of this multiplication, and it is what causes the wire loop to rotate. We also use the right-hand rule as a model. It allows us to visualize the direction of each component of the equation. To do this, we pointed the middle finger of our right hand in the direction of the current, and our pointer finger in the direction of the magnetic field, which in this case was upwards. As a result, we could see which direction the force would be in, which would tell us what direction the loop would spin in.
Here we have the pictographic models of the experiment. On the left, we have the system schema. The wires and the magnets are shown as being the only objects inside the system. There was a magnetic force between the magnets and the wire, as well as between the magnets and the batteries, and there was an electric force between the batteries and the wire, as well as between the batteries and the magnets. On the right, we have the force diagrams. The left force diagram is a hypothetical scenario. If the wires were not stripped at all, the wire loop would not spin because there would be no current running through the wire. The right force diagram is closer to our actual experiment. One wire was stripped completely, and one was stripped on only one side. If both wires were stripped completely, the loop would have spun because there would have been no current running through it, but it would have made only half a rotation before changing directions, because the permanent magnet repels both the north and south poles of the wire loop. By stripping half of the wire, the current is turned off for a portion of a rotation when one pole nears a magnet. The momentum from the previous rotation keeps the loop moving, and the force of the magnet on the far pole of the wire, north or south, takes over again, keeping it turning.
We designed an experiment in which an electric motor was made using batteries, wires with alligator clips, magnets, clay, and a wire loop so that they were in a circuit. 3 trials were completed to test the current's effect on the rotation of the loop. Trial 1 contained 1 battery, Trial 2 contained 2 batteries, and Trial 3 contained 3 batteries. Videos were taken in slow motion so the rotations per minute of the loop could be counted for each trial and a graph could be created from this data. We had to assume that the current is proportional to the number of batteries, that all magnets are of equal strength, and the batteries kept the same voltage throughout. We predicted that as the number of batteries increased, the number of rotations per minute of the loop would also increase.
The results of our investigation are shown here. We found that as we increased the number of batteries in the circuit, the number of rotations per minute of the wire loop also increased. Interestingly, the number of rotations per minute increased by 4 each time a new battery was added. The graph we created from this data produced a linear or proportional relationship between the number of batteries and rotations per minute of the loop.
One potential problem innate to this experiment was counting the rotations of the wire loop with the naked eye. There was no other method by which to count the rotations, but there was no way to verify the accuracy of that count. A potential solution to this problem would have been to use Tracker to count the rotations instead. Some possible sources of error could have been miscounting the rotations of the wire loop or not stripping the wire entirely. However, the graph derived from our data showed no sign that these mistakes occurred, though they are still possible sources of error.
To compare a model with a brushed DC motor, we can look at the similarities and differences. A DC motor has a rotor positioned inside a stator which contains north and south ends of a magnet, while our model is positioned above a stack of magnets. Both types of motors require a battery to run, however, the type and number of batteries may vary between models. The wire loop in our model is synonymous to the rotor and brush in a brushed DC model, but they are structured differently because the rotor in the DC model includes windings of wires rather than a loop. Ultimately, both models do need current to run. The physics behind our experiment starts with the stripping of the wire loop. Only one side of the wire was stripped so that even when current reached the side that was not stripped, it would still contain enough force to push the wire from the loop of the side that was stripped. The magnetic field and current work together in the circuit that allows a magnetic force to be created, as shown by the equation F equals IL times B. This force pushes in one direction on one side of the loop and the other direction on the other side of the loop, causing a spin motion. Lastly, as we added more batteries to our circuit, the current increased. Our current was Our circuit was parallel and contained no resistors, so as more batteries were added, the charged particles in the circuit could move more quickly, which allowed more charges to be in one spot in the circuit, which caused the electric current to increase. As found in our results, this increase in current increased the number of rotations per minute of the wire loop.